My apologies. This stream will start about 15 minutes into the lecture. And I need to get back to the board that is relevant for this lecture. Let me just start with the example that I was just on, and hopefully people can follow from the AWW app. And if you're seeing this and really need the 15 minutes, that's also in part why I said there will be office hours. My apologies, I went through the steps to stream it, and well, it didn't stream. In fact, it didn't stream the second time, only the third. I guess I wasn't patient enough. Okay, so to sort of get folks who might be new to this, if you're looking at this downloaded from the YouTube stream, you need linking with correction to give all of, we're going to construct homomorphisms from the homotopy of our space, which I'll often think of as a manifold, into, Q, but we're going to define integer invariants, but then we'll get all of the ones to the rationals. So let me recap what we have so far. Suppose I just have a map from a 3-sphere to a 4-manifold. And that 4-manifold has 2 submanifolds. And morally, if you're doing homology or cohomology, they're disjoint. So they're Poincare dual cohomology classes cup to 0. And in the quote unquote catch-up lecture, I gave a concrete formulation of what I mean by the Poincare dual cohomology class at the cochain level. So, because what you need to do, and this is Sullivan's insight, is really work at the cochain level to recover more of the homotopy type of your space. So what happens here is that the cup product is 0, and then the claim is that if I take a map F and look at its pre-images, so let me just sketch here. Here's my S3. And suppose I have my M down here. And it's got the V and the W. And they do intersect. But let me actually make W a different color, sorry. So I've got V and the W, and they do intersect, but that intersection is the boundary of this T, okay? Then what I can do is look at the pre-image of V and W. So V is codimension 2 in M. Its pre-image is going to be codimension 2 in the sphere. In other words, a 1-manifold. And then W is codimension 2 in M as well. So its pre-image is also some 1-manifold. And that means I can take the linking number. And again, the way I'll do that is choose a co-bounding of the pre-image of V. And so this linking number is take a co-bounding of the pre-image of V and intersect it with the pre-image of W. But I'm going to have to correct that by looking at the pre-images of T. And what I wanted to do is explain that correction term, and then we'll make, and I'll see how this this then gives us something, a precise big picture. So let me redraw my S3. Well, now let's suppose we have a homotopy. So let's think about what happens through a homotopy. So in this homotopy, I won't draw M again, but I'll draw the homotopy. So I have my, my linking that I'm counting, as well as the pre-images of T, which I'll draw in yellow here. So here's the pre-images of T, and they can come with different signs maybe. And then maybe there's some linking as I just drew. Okay. And what can happen through a homotopy? Well, this linking is well defined because, again, under transversality assumptions that I'm generally not addressing throughout, the V and W can intersect, but that intersection is a finite collection of points in M. So that intersection has codimension 4. So S3 can't see that. The pre-image of something codimension 4 and S3 under transversality is empty. That's the only negative one-dimensional manifold. But S3 cross I is 4-dimensional. So it can actually sort of, if you will, witness that intersection. So through the kind of cobordism that comes here, and it really can be a cobordism, through that cobordism, at some point, the green and the yellow could separate because they can intersect. And S3 cross I, that's just allowed to happen. But V and W intersect in the boundary of T. And so what would also happen is one of the points that we were counting in the pre-image of T would have a one manifold attached to it that, that would co-bound that intersection. And maybe some others go through here. And again, some linking could be preserved. The point is that if we look at the two terms, let me bring it back down. If we look at these two terms, the linking number and the pre-images of T individually are invariant, but their difference, or maybe there's some, but I'm pretty sure it's their difference in this case, their difference is invariant. So let me just say that again. So the number, the linking of the pre-image of V and the pre-image of W, and the count of the pre-image of T individually can change. But the difference is invariant. Okay, so hopefully the people who've started late through YouTube can follow that example, because in fact, so all of pi star x is, well, let me, tensor Q for a simply connected x is seen through linking with correction invariance. So that's kind of a remarkable fact about rational homotopy theory, that if you wanted to understand concretely the homotopy of X, there's various ways you can calculate it. I'll talk about that a little bit with Sullivan models and Quillen functors, but the way to measure it, if I give you a concrete map, quote unquote, concrete map from a sphere to a space, at the end of the day, it's all these kinds of formulas with taking pre-images, co-bounding, intersecting, and counting. So let's now see how some formalism lets us make this precise. So here's some questions. So, how do you find these? What are relations? et cetera, et cetera. So here's where the bar construction, so remarkably, these are governed, these linking invariants are governed by bar constructions. All right. Let's see. So there's a question in the chat. Should one think of the corrections as some underlying higher structure, least structure, but higher L infinity? Yeah, the way I would say is the 0th order invariant is, in this setting, is pull back your cohomology from X and evaluate it on the fundamental class of the sphere. And that's just the Hurewicz image. And then when that vanishes, then you can take a D inverse, and now we multiply. And then if those vanish, you can take a D inverse and multiply. And the first example I did, and again, my apologies to people who came late, with the PQR, that first example was a case where you would have two D inverses. So absolutely, this is, if you want to use this kind of language, this is a derived version of just evaluating cohomology on homology, in this case, the homology class given by the image of the fundamental class of the sphere under your map. So that's a perspective that I want to emerge. But let me again be concrete. So last time, because we talked a little bit about loop spaces, we talked about the bar construction, and the bar construction. So if A is a differential graded, all I needed is associative algebra. Then the bar construction, I've got the direct sum of tensor products. You really want to think about this as the cotensor coalgebra, but I won't need that quite yet. And then you've got a differential, which I'll be brief, and so I can take dA1 bar A2. You're using the Leibniz rule. Etc. But you also, because we have an algebra, you can use your algebra structure to get another differential. Namely, I'm going to remove bars between elements and let the algebra elements multiply. So that's the convenience of the bar construction. And there's signs all the way along. So so now we're going to look at so I'm going to have some map from a sphere into M, say, or X. And I'm going to let my algebra just be the cochain algebra, which, by the way, is associative at the cochain level. It is not commutative, but it is associative. So I can look at the bar constructions. And by the way I like to think about the bar construction, I like to put it on a, as do most people, like to make a bicomplex. So let me scroll up. So here's the bar construction on the cochains of M. And I have, things like cochain 1, cochain 2, cochain 3. And then the differential comes in two pieces. This is the D alpha 1 bar alpha 2 differential. But then, and notice that I've already run out of real estate a little bit, so let me give myself a little more real estate. The other piece of the differential comes over here where I remove bars So the bar complex has this little bit of geometry to it. It sits in a second quadrant, and the differential has a piece that goes up and a piece that goes down. And what we're going to do with this bar construction is we're going to, well, if I've got a map F, then I can pull back cochains and then look at the impact on the bar construction. And that's going to land me in the bar construction on the cochains of the sphere. And then, as I'll do first in an example, well, so the point is, then I've got things like F upper star alpha 1 over here, bar F upper star alpha 2. And again, following Pedro's comment, I said this is kind of going to be a derived version of pull back and evaluate. But I don't know how to evaluate this expression. So what we're going to do is notice that in the bar construction on the sphere, this is going to be homologous to, we're going to find something that we can evaluate. So that's the goal. And let me give you an example. Let's do the example for the 4 manifold. And then I've got my V and my W. And I like to think about these are tome cochains. And then I've got my T, and then the co-boundary of this tome cochain for T is basically tau V cup tau W. I won't tell a lie, but I won't sort of say what, there's a co-boundary term that I'm missing if I really want to think intersection theoretically, but great. That's just, so now let's picture the bar complex on M. And I claim that there's a co-cycle that looks like this, that I have tau V bar tau W. And then this differential is 0 because the boundary of V is empty, and that's also the boundary of W. This will be bar tau V intersect W, again, up to a term that then I'll ignore for the moment. But that is also the boundary of this tau T, because boundary of T equals V intersect W is being reflected here. So then this object that I'm highlighting in yellow is a cocycle in the bar complex, okay? These two terms each have two separate boundary terms. I guess I should also then say that this one has, if with no bars, then you just set that boundary to be 0. So the sum or difference is going to be the cocycle. I think it should actually be the difference or the sum. So if I've got a map, then I can look at the image of this cocycle in the bar complex on the sphere. It would be, oops, S3, not S4. And let me give myself plenty of space. And the pullback is just sort of a formal thing. It's really just pulling back the cochains, and then just extending all the structures. So I've got f upper star tau v bar f upper star tau w. And then I've got my f upper star tau t. And sorry, let me give myself a little more space. I just know I'll need it and it'll help. This is all again happening in the bar complex of the cochains of the three sphere. Okay. And again, you say, well, I don't know how to evaluate this kind of expression on the fundamental class of the three sphere. But this is in total degree 3 if you, so this calculates the homology of loops S3. So that's why, which is a copy of Z in every even degree. So part of why I introduced the bar complex in the catch-up lecture is that a key fact is that it calculates the homology of loop space, in this case, loops S3. So I know, and in degree 2, things are represented. This is a key point. So in degree 2, this is going to be spanned by bar, I don't know, just call it iota, where iota is a generator of H3 of S3. So this term up here that I'll underline in yellow, it's in, so yeah, I didn't talk too much about degrees, but the total degree is going to be the total degree of the forms that you have, or the cochains, minus the number of bars, and then minus 1, I guess. Well, or yeah. And so this is homologous to something down there, and the game we're going to play is find some homology of it. So look, this f upper star tau v is 2 cochain on S3, right? And so that means that it is, and it's a 2 cocycle, so it's 0 in cohomology, so it's the boundary of something. And so what you can do is find a D inverse f upper star tau v. And this term, if I look at its boundary, I've set it up exactly to kill the pullback, f upper star tau v bar f upper star tau w. But then it has a second part to its differential, namely my apologies. It has a second part to its differential, namely what I get when I remove the bar and multiply. So that would be D inverse f upper star tau v times cup or whatever f upper star tau w. So this becomes a term that then gets added to that term. And my original cocycle is homologous to this sum. And lo and behold, this was our invariant. So the invariant was, in fact, count the preimages of V. Let me switch from tau to just V itself with the preimages of W, and then subtract the preimages, the count of the preimages of T. And that is exactly what this cochain is. So this is the value of the cochain that I just circled in yellow. On the fundamental class of S3. Okay. So let me give some mottos and then I'll move over here. So what we just did was we took the bar construction. So we have F from Sn to X. We took the induced map. We took the induced map from the bar construction on the cochains of X to the bar construction on the cochains of Sn. Again, for people familiar with this area, that's just taking the induced map on loop spaces. And for people very familiar with this area, that makes sense because rational homotopy is sort of seen perfectly through homology of loop spaces. That's the Chen approach to rational homotopy theory. But then the result has mixed weight, but must be so we have F from the sphere to X, and we're looking at the maps on the bar constructions, but let's say gamma is a cocycle in here. The result, F upper star gamma, has mixed weight because gamma does. But must be homologous to an expression with no bars, or only outside bars. In other words, weight 0. So we can, by abuse, or let's see, we call that result F star gamma hat or something like that. And then the Hopf invariant of F coming from gamma, defined by gamma, is going to be the invariant that sends F to take this F hat gamma and just evaluate it on the fundamental class of Sn. So there's a good question in the chat. We could have done the same with, there's not a canonical choice of this F upper star gamma hat. I could have reduced with respect to W instead, taking the D inverse of tau W. Absolutely, there's a lot of choices. It's pretty easy to see that any two choices for F upper star gamma hat, they actually must differ by D of something in the bar complex, but because they're in weight 0, that means they must be homologous cochains. So this is actually independent of the choices so far. And in fact, there are further relations, which we'll get to in a moment. But then, yeah. But then let me say that the one thing that Ben, Walter, and I prove is that the map from the homology of this bar complex on the cochains of X to hom pi star X. Now this was actually into Z. This has, and again, this is just sending gamma to the homomorphism, which takes F and looks at this pullback, reduces it, and evaluates, has finite co-kernel. So it's an isomorphism up to some sort of finite amount. Let me make this a little bit bigger. My apologies that So in fact, what you can do, this is the Hopf Invariant 1 co-kernel. For spheres, it's 2 unless the sphere itself is S3 or S7. Now we can ask the famous Hopf Invariant 1 problem for any space. You're looking at this in a lattice. What we really want to then say is that once we tensor with the rationals, this is basically an isomorphism. Although that's not going to be quite true. Let's see. Let me pause and ask, because we don't have too much time, and I do think it would be helpful. Let me say one other thing. So again, these the ingredients, this weight reduction has, well, 3 ingredients if you want. You pull back, that's your initial ingredient, and then everything else is just take D inverse and then, you know, your product cup or wedge or intersect, if we want to think about it that way. So, so that implies the resulting invariants are, well, as advertised, linking with correction. So it's this theorem that that then is the main focus. And again, we now see that this bar construction has a lot more kind of geometric content than you would think at first. It's but now that we think about co-cycles, what they're really coming from is vanishing of products. At the most basic level, that can happen to disjoint things. So Nir asks if we can see torsion in homotopy groups with linking. The linking is much more about you could reduce these mod P, but you don't get too much that you wouldn't expect to. My dream is to one day understand, is to measure the torsion in homotopy groups through quote unquote self-linking. That's kind of the point of about 3 or 4 different projects I'm working on, and something that I would deeply love to start seeing the torsion. But let's satisfy ourselves now with the non-torsion piece. So what do I want to say? Well, let me just preview next time. So the kernel, there is kernel. And it's because we're using the wrong bar construction. Well, it's the right one if we want to get things over Z. So for example, alpha 1 bar alpha 2 sort of minus plus alpha 2 bar alpha 1. If suppose we're in de Rham theory, this would always be so that means we're commutative. This would always be a cocycle. But the linking invariant would be 0. So I think where I'll start next time, the main point is we replace this bar construction for associative algebras with a bar construction based on Lie coalgebras, which only works for commutative algebras. And then your theorems are sharper. And then the fun thing is that this has a model. The combinatorics here are basically based on, grounded in the homology and cohomology of configuration spaces. So that was another, there are a couple of things I talked about in the catch-up lecture, and cohomology of configurations was one of them. The bar complex was another. I think what I'm going to do is, well, I won't stop sharing or stop live streaming yet. I will pause and answer questions for a little bit. Again, I can try to start navigating the even unmuting people. And then if you have a question that you don't want on YouTube, what I will do at some point is stop the recording, but then continue on here a little bit. I won't stop sharing my tablet, because that'll be how we can answer questions. So yeah, so I'm going to pause now for questions. Let me see if I can. Let me see if I can see everybody's. See the list. That way I could potentially unmute people. Sorry, I'm trying to, there we go. So now I do have the participant list. You could, for example, raise your hand or message me and I could unmute you, or you could also just text a question in the chat. Any questions? They can also wait for office hours or potentially email. Yes, the note from the lecture will be saved as a PDF. And I did, in one of the emails I sent, it's just going to be a simple directory URL where they will be there. So absolutely, these notes will be available. And that way, you know, people could just listen to only the sound, look at the PDF, and they don't have to worry about taking notes. Other questions? And another one, sorry. Our lecture is based on any papers, preprints that are accessible. Yes. So, and I'll maybe try to say, put together a little bit of this, but all of this material is in a series of 2 papers. The most relevant one is Lie coalgebras and rational homotopy theory. Series 2 in the paper does the Hopf invariants, but you would need to understand some of the things from the first one. Let me move this. Next question, non-math question. What hardware am I using? I'm using a tablet, but then I'm within Zoom, I'm sharing a browser that is showing what is on my tablet because it's shared. And I know some people are looking at that web page directly. So that's, and then what hardware am I using? So I am beholden to Apple. It is more expensive, but an iPad with an Apple Pen does keep things looking good. I mean, just the fact that it's flat and I can write normally makes a big difference. If things are up in front of me, I tend not to, even with a tablet, it tends not to look as good. It makes a difference, at least for me personally, to be able to write down on the flat surface. What precisely do I mean by mixed weight? So mixed weight is, for example, you know, F upper star tau V bar F upper star tau W minus plus F upper star tau T, and then uniform weight would have just like, you know, I don't know, it could even be theta with a single bar, minus plus, plus minus F upper star, mu or whatever. There's just the same number of bars around every term. Yes, thank you, Pedro. Do the computations depend on the fact that the homology of loops has many holes? Yes. So you can, yeah, so target, I would actually say it's domain. Yeah. Yeah, let me just say, let me give you, and I'll say this again next time. A vague conjecture is this should be true for all of the maps from a space X into a rationalized space Q. What is true? It should somehow come down to kind of linking with correction again. But it would be more local. If you think about X as a wedge of spheres, somehow you don't have complete vanishing in a bar complex. It's sort of at one homology class at a time. Ultimately, I think there's some Maurer-Cartan kind of formalism that this would work out. But I've had this conjecture in my head for years and years now, and worked on with a couple people, and we still don't have the right idea. And I should also mention that next week which I will next week as well, that these D inverse integrals are things that also arise in some of the field theory. So somehow I think what's ripe is finding the right kind of approach that marries this very explicit linking with something like a Maurer-Cartan formalism, along with these integrals that you can explore using these ideas from physics. So I think those all would go together for maps between spaces, but that's right now much more of a hope than anything that I've made substantial progress on. Great. I think I'll take the pause in comments to stop the live